You've heard me in previous videos make references to the fact that there are times when you shouldn't use floating point numbers, especially if you want particularly exact results. And that's because of one of the trade-offs that we have to make when we work with floating point data, which is the types float and double provide us the ability to store things that look a lot like real numbers. And they can store a massive range of different values. But the values are spaced out across that range in a way that means that there are some values that cannot be represented exactly. And so the way we typically couch this in 111 that you might recall is that when you work with double, you can be guaranteed 15 significant digits in a decimal sense, so in base 10. You get actually a little bit more than 15, but you can be assured of getting 15 significant digits. If you work with float, you get 7 significant digits. There are larger floating point types that you can get more significant digits with, but we think about it that way because we're used to scientific notation and we understand that if we work with a certain number of significant digits, we can't necessarily represent all numbers in a particular range because, of course, in any given range, there are an infinite number of real numbers. So if I ask questions like how many real values are there between 0 and 1? The answer is, well, we can't count them. They're uncountably infinite. Okay, so as a result, because computers cannot store infinite size things, we instead have to put up with this compromise where a floating point value on a computer is a little bit inexact. There's a little bit of precision missing, and that's generally not a big deal for us because if we know that we have 16 significant digits or 15 significant digits, we just have to make sure that our calculations stay within that. The issue is, when I do a calculation with a floating point value, like this one, the calculation yields a result that is also a double. And the double can be stored in 15 significant digits. That means that when I do the calculation, I have to chop the result down to be 15 significant digits. That might introduce a small amount of error into the result. And if my calculations go across millions and millions of iterations, like I have here, that error can pile up. And it isn't really that big of a deal if you know how to work around it. And again, as I've done many times, there is this entire course that many of you will end up taking that does talk about that, about how to write numerical algorithms that work, that we can rely upon to be accurate, among other things, as well as the inner workings of floating point data. We're not going to do that because I don't want to rain on their parade, and because I would just spend hours and hours talking about that and get off topic, which I'm already at risk of doing. I do, however, want to at least show off one relatively minor, but I think also very accessible example of that error actually becoming visible. And that is, I want to evaluate this equation here, which is obviously contrived. And of course, if I wanted to do this in a programmatic sense, I would just write this assignment statement. That's a sensible thing to do. The reason I'm using a contrived example is because I want the calculation to be simple enough that you can see what the answer is supposed to be without needing to work it out on paper. So y is the value 1 over 5. Notice that x is basically an integer, and y is a rational number. It's not like an approximation of pi or something. Y is a number that's an int over an int. So it's a rational number. Integer numerator, integer denominator. And then what I'm doing is evaluating this equation by taking the value 1 over 5 and just adding it to z 5 million times instead of multiplying it by 5 million. I add x, I add y 5 million times, and I subtract off x. And then I try and convert the value of z to an int. The reason I think that's a good idea is if I stare at this equation, okay, so mathematically x then minus x means that the x's cancel out. So I get 5 million times y. Well, y is 1 over 5. So 5 million times 1 over 5 should be the nice round even number 1 million. It should be mathematically exactly 1 million. So I expect when I'm done, given that looking at this, I'm not working with 16 significant digits. None of these numbers need that much precision. I'm well within the comfortable range of a double. I should expect that z is the integer 1 million when I'm done. And so I'm going to convert it to an int and print it out. I'm also going to convert it to a string and print it out directly. I'm going to try and print z directly. The reason I'm not doing, I guess I'll add one more print statement just to show my work here. I could just print z by pushing it directly into cout. The problem is that when you print a double to cout, it expects that you're working with numbers that could be imprecise and tries to round them off for you. And I actually want to deliberately avoid that. ToString doesn't do this. ToString tries to give me a certain number of decimal places. And yes, for those watching that happen to already know this, it does turn out to be the case that you can tell cout how to print floating point data, but I don't want to get into that right now. Okay, so we'll run this. Okay, so you can see when I print out z with line 28, it prints it with this scientific notation, 1 to the power of 1 times 10 to the 6. It's covering up what's actually happening in a decimal sense there. So when I convert z to an int, the value I get is 999,999. I want the number 1 million, I get the number 999,999. Now, maybe you could argue that's not that scary because we know that, converting a double to an int might chop off a decimal point. The true value of the number is this. So 999,999 point some stuff. And you could argue that's pretty close to 1 million. But hey, what if I went up not to 5 million, but 50 million or 500 million? There would come a point at which the position after the decimal point is like 2 or 7 or something, not 0.9. This actually should worry us a little bit. I've done a bunch of operations, not really that many in the grand scheme of things, and ended up with a result that seems to be going off. It seems to be slowly diverging from what I want. Those errors are going to pile up. So what do I do? Well, in general, as I said, there's a whole course you can take on this, numerical analysis, that talks about how to write algorithms where, although you know there will be some error, you can keep it under control. You can know what the error is going to be and keep it under control. But there are cases where you're writing algorithms where the algorithm gets complicated enough that doing that is pretty difficult, even after you've taken that course. One example is a course I teach occasionally. I'm teaching it again in the coming year, CSE 445. A part of the course involves a lot of numerical algorithms that have a huge number of steps. And as the steps go on and on, we end up with these errors piling up. And it can really be a big deal because part of the algorithms that we work with also ask yes or no questions, like is the number less than 0? And when these errors pile up, you can end up with a number that mathematically is supposed to be equal to 0, but ends up looking sort of close to 0, but not actually 0. So mathematically, this might be supposed to be 0, but the errors pile up and it's a little bit negative. And that can make a big mess in the context of, for example, a linear programming solver like we would write in CSE 445. Now that's whatever. Go take that course. It's lots of fun if you want to know about that stuff. What I want to talk about now, though, is a good application, I think, of classes and abstraction that give us a sort of middle way. So I think to myself, I like working with real numbers because for working with a bunch of, observational data or something that might just be a bunch of digits with a decimal point in them, what I'm working with here is a bit more structured. I'm sort of working with fractions. And I think to myself, if I do arithmetic mathematically with rational numbers, so I don't bother using decimal points, I can do exact arithmetic with fractions. That is to say, what I have here when I talk about a fraction is a fraction with an integer numerator and an integer denominator, a rational number. So I could, for example, view 1/2 plus 3/4. Well, 1/2 is just 2/4, so that's 2/4 plus 3/4, and now that they have a common denominator, I can add them together. That's 5/4. Notice that if I work with these fractions, with these rational numbers, everything is always an int on the top and an int on the bottom. And I can do actual calculations, like adding the two fractions together, and end up with a fraction result that is still an integer on the top and an integer on the bottom. Never do I need a decimal point. What I end up with, so fraction plus fraction equals fraction, basically. And of course, I can also multiply them together. So I could say 1/2 times 3/4. So how do I multiply fractions? So this is covered by a prerequisite of this course. I think it's like 5th grade or something. So 1 times 3 is 3, and 2 times 4 is 8. So 1/2 times 3/4 is 3/8. Notice again, fraction times fraction equals fraction. And so I realize if what I'm worried about with this example was the weird rounding errors that occur because of the inherently imprecise nature of floating point calculations, given that what I'm working with are a bunch of ints and fractions, why not just do everything with fractional arithmetic? Well, one reason is I don't want to have to keep track of all these numbers. So wouldn't it be great if there were a numerical type halfway between int and double, sort of a way of representing a rational number, a fraction that I could do arithmetic with? Well, okay, there isn't. I'm sorry. C++ doesn't come with such a thing. But thanks to the magic of classes and abstraction, I can write that type myself. And if I do it properly, I can get a perfect abstraction. So here I have a main function. And before we get started, I'll show off what I have so far. So what I want is the ability to write this class called fraction. When I create a fraction, I use a constructor, and the idea is the constructor is the numerator and denominator. So this is meant to be the fraction 6/10. And this is meant to be the fraction 3/6. Now, a future video will observe that 3/6 is actually 1/2. Wouldn't it be great if we could remember it that way instead of as 3 over 6? But we're going to take small steps. So I want a type called fraction that represents a fraction, a rational number with an integer numerator and an integer denominator, where also we will impose the restriction that the denominator cannot be 0, because that wouldn't make sense. You can't divide by 0. But I don't just want that. Obviously, I could use a struct in C for this. I don't just want the type to be called fraction. I want it to behave like a number, because it is. 3 over 6 is a number. I want to be able to print it out like I can print a number. I want to be able to add them together like I can add fractions. I want to be able to multiply them and divide them like I can work with fractions. I want it to be a perfect abstraction for a number. I want to make my own numerical type that does rational arithmetic. And I can. I can make a type, I can make a class that stores the fraction, I can define a bunch of operators to give me all of the features that I've grown to know and love with regular arithmetic in C++. So let's do that. Before I get started, I need a bunch of operators. One operator that I have provided already is the operator to print a fraction out. So I'm going to compile the unmodified code just to see what works going into this. Oh, whoops, I named the file wrong. Okay, so it compiles with lines 58 through 60 commented out. There we go. We can see it prints out X, Y, and Z. And now I can scroll up and show off what we've got. So currently I've got this fraction class, which has a constructor that takes a numerator and denominator and then initializes the members accordingly. It verifies that the denominator is not 0 because that wouldn't make any sense, and it prevents the construction from completing if that's the case. There's a function to get the numerator, to get the denominator, and a function to return a double representation. So the fraction can convert itself to a real number if needed. The way we do that is we just take the numerator and divide it by the denominator to produce a double result. Recall that if I just wrote this, I would get int over int, because numerator and denominator are both ints. And that would just be probably, that could be 0 if it's 6 over 10. So I do this to force one of the operands to be a double. So I get int over double, which we know equals double. Okay, so that's the fraction class. Just a simple way of storing this pair of a numerator and denominator and verifying that the denominator is non-zero, and also imposing some access control. So once the fraction is created, its values are permanent. So you can't modify them. You could make a new fraction if you wanted, but you can't modify the values inside an existing fraction. And we're going to come back to fractions a few times over the course of the week. Now, down here, I've got a print operator. I thought about writing that in front of you, but I've realized we've seen that in other videos. Let's just not spend time on that. So here I have an operator that prints out a fraction. So if you push a fraction into an output stream, like I'm doing down here, you will just get numerator over denominator. So it gives us an easy way of printing stuff out, which will be great for if we want to debug stuff. What I want to do now is define arithmetic operations that allow me to work with fractions. I want to see what happens if I add x plus y. So wait a minute, what is 6 over 10 plus 1 over 6? How do we do this? Well, there are a few things we can observe here. So normally if you want to add two fractions together, what you do is put them on a common denominator. So if I can get the denominator to be the same, and I guess I can show an example of that. So 1/4 plus 2/4 is, well, let's see, that's 1 plus 2 all over 4, which is 3 over 4. Notice how, because the denominator is the same, it is pretty easy to add them together if I can get the denominator to be the same. Okay, so what do I do with 6 over 10 and 1 over 6? Obviously, they're not on the common denominator. I can put them on one. I can multiply both fractions by things that don't really change them. I can rewrite both fractions, I guess, in a way that puts them on a common denominator. So I could try something like this. I could say, well, what I could do is I'm always allowed to multiply by 1. So at all times, I can multiply anything by 1. I can choose to write out my 1 however I want. So the way I'd put these two fractions on a common denominator would be to say, well, you know what denominator might work is 6 times 10, 60. So I could say, let's see if we can put everything over 60 here. Okay, so what does this equal over 60? How am I going to do that? Well, I have to put this fraction over 60, and I have to put this fraction over 60. So I'll do it like this. So I'll do 6 over 6 times 6 over 10. Notice that 6 over 6 is just 1, and I'm allowed to do that. And the reason I chose 6 over 6 is if I want this to be over 60, I need to make the bottom 60. So I have to multiply the bottom by 6. If I multiply the bottom by 6, I have to multiply the top by 6. The same logic applies over here. If I want this to be over 60, I need to multiply the top and bottom by 10. So I would do 10 over 10 times 1 over 6. Okay, so what does that give me? Okay, that gives me, so 6 times 6 is 36 over 60, and then that gives me 10 times 1 is 10 over 60. Okay, so then I have 36 plus 10 over 60, or 46 over 60. And that is the result. 6 over 10 plus 1 over 6 does equal 46 over 60. You might stare at that and think, there is another way of writing that. It could be, for example, 23 over 30. Sure, fine. We'll talk about that in the next video. For now, this is the correct answer. There might be more than one way of writing it, but this is the correct answer. So I can add fractions together by putting them on a common denominator. Okay, how do I do that in general? Before I actually go to writing the operator, we have to know how to solve this. The reason I like this application is this video is almost me doing a 116 assignment in front of you. It gives me an opportunity to talk about like solution methods, not just how to write operators. So how do I compute a over b plus c over d? Okay, well, I want to use the same logic I just used, but with arbitrary fractions, so a over b and c over d. What I might do is something like this. I want a fraction with a common denominator. Well, one thing I know that's common is I could write something, I could try and put everything, just like how I took when the denominator was 10 and the other denominator was 6, I went over 60. I could try and put the whole fraction over b times d. So the question is, what do I do to get my fraction to be over b times d? Well, I need the thing on the left to be over b times d, so I have to multiply the bottom of the left by d, and I have to multiply the bottom of the thing on the right by b. So I guess what I want to do is something like this. d over d times a over b plus b over b times c over d. And that gives us what? So that gives us AD over BD plus BC over BD. This is actually, there's a lot of different reasons one needs to do this in mathematics. You might notice when you see AD plus BC, that shows up in a lot of other contexts as well. And so I end up getting this. There is my derivation for how I add together two arbitrary fractions. Because we know that the denominators of both are non-zero, this operation should always be possible if I have two fractions. Now the question is, how can I actually write the operator? So for now, I would like to write the plus operator for two fraction objects. Okay, so there's a prompt that tells me to do it up here. And we're going to come back to this a couple of times. I'm sorry that my text, that the comment is obscured a bit by the text on the screen, but I'm going to leave it up. I want to define a plus operator, the binary plus operator that takes two fraction objects and returns another fraction object. So I'll do that like this. It's going to return a fraction. It's going to be called operator plus. As I said in previous videos, don't worry about memorizing the way of writing out the signature for every operator in the world. There is a list that's linked from the notes alongside the video. On an exam, you would be expected to know how to write a plus or minus operator or something similar, but you'd be given advance notice as to what the exam would require. You wouldn't, for example, be thrown into writing one of these out of nowhere on an exam. You should know how to write plus and minus and multiplication and division, because we're going to write those a few times. You should also know how to write less than. We've already seen an example of that, but the more exotic ones, if you need them, will tell you what to do. Okay, so I want to take as my left argument a fraction, and I'll take it by constant reference, just to right off the bat. I will call that left, and I'll take my right argument also by constant reference, and we'll call that right. And I'm sort of at war with the text on screen here. I want to leave it up because it's my derivation of what I'm going to do. So I know how to compute the sum of a over b plus c over d. So what I'm going to do is actually use variables named a, b, c, and d. So I'll say a is the numerator of the left. B is the denominator of the left. And I get it that this is obviously a little bit verbose. The idea, though, is that in general, when you want to implement some mathematical thing like this, doing it on paper or on digital paper, like I've done over on the right here, and then translating that to code is a lot easier if you use similar notation in both. And also because once I write this, I can always copy and paste it in the other operators that I write. All right, so I get the numerator and denominator of each fraction. I just call them a, b, c, and d. What do I want to produce? I want a new fraction containing my result. Well, we already saw the result is this thing here. A over b plus c over d is ad plus bc all over b times d. So I'll make a fraction for my result. The numerator will be a times d plus b times c, and the denominator will be b times d. There we go, and I return that. And whether or not you think this operator looks a little bit ugly, you'd hopefully agree with me that once it's written, it's done. Like once I get this operator working, anybody that wants to add fractions just writes x plus y. And it's good. They don't need to worry about how ugly my code looks. And again, that's one of the reasons why these features are so helpful in C++. It gives you all of these tools. Some of them are hideous, but when you use them properly, in accordance with abstraction and encapsulation, you can write this one hideous thing and hide it in some library somewhere, and the people that use it get this beautiful abstraction as a result. So we'll try that out and see what we think. All right, and so here, x plus y, 6 over 10 plus 1 over 6 is 46 over 60. And now I'll clear my derivation. So recall from what we talked about a minute ago, 6 over 10 plus 1 over 6 equals 36 over 60 plus 10 over 60, which equals 46 over 60. We'll talk in the next video about how to reduce fractions to lowest terms. That's a different question. And then y plus z, so 1 over 6 plus 3 over 6. You might observe, of course, you would look at this as a human and say that's 4 out of 6. But you could do it the full way with the derivation we just used and get, well, let's see, if I put them on the common denominator it's trying to use, which is 36, okay, well, that's 6 over 36 plus 18 over 36, which is 24 over 36. Which actually is 4 out of 6, as you might notice, and we'll again talk in the next video about how to get things into lowest terms. But this is the right answer. I am able to add fractions now. So I have figured out how to add fractions. And once I have written the operator, I get to use my fraction object as if it were a numerical type, which is a really big deal. Okay, one more thing. We have to do the multiplication operator. I guess before we do that, there's no test for it, but maybe you'll take my word for it. I want to write a subtraction operator too. So to subtract, we'll do operator minus. Okay, so operator minus is the same as operator plus, except instead of adding the fractions, I am subtracting them. So there we go. That was pretty easy. And you can verify that our derivation from earlier still works there, but the executive decision, I guarantee you that it does. So I have a minus operator now. I want a multiplication operator as well. I'm actually going to copy and paste for that too. I'll just make some adjustments. Okay, so I want to write the operator multiplication. So how does that work? Well, let's take a look. A over B multiplied by C over D is just going to be AC over BD. Okay, so that's a bit easier. So fraction result, and I initialize that to A times C on the top and B times D on the bottom, and then I return it. And you might actually realize there's a one-liner notation I could use here. I'm using 2 lines because I think the example might be confusing enough as it is. Okay, so here I've got my multiplication operator, and then finally I guess I want to do division. So we'll implement that operator as well. So operator division, and then we just have to derive that. So what does it mean to divide one fraction by another? So A over B over, I guess, over C over D. Okay, well, so that's actually going to be, and we could also write that, depending on your notational taste, you could write that as A over B divided by, oh, this looks so ugly, C over D. As I'm sure you recall from one of the prerequisites of the course, again, somewhere around 4th grade or 5th grade or something, that will just be this result here. I want to erase this. It looks so bad. That will just be A times D and B times C. A times D over B times C. And so we'll just program that in. So it'll be A times D and B times C. There we go. I've now got the 4 cardinal arithmetic operators for my fraction objects. There are only tests for a few of them. We're going to come back to this in previous examples and see some of the other operators. And of course, you can add your own. Look at the posted code. And now it compiles, and let's see. So x times y. Okay, so x times y would be what? It would be 6 over 10 multiplied by 1 over 6, which should be 6 over 60. Not in lowest terms, but that is the correct answer, and we can see that's the answer here as well. And so I have been able to write this fraction type that now can behave just about like a number in a lot of common use cases. I can write x plus y. I could, in fact, if I wanted to, write something like, let's try it out. I could take the result of x plus y and multiply that by z. So I could say, what if we compute x plus y all times z? And we'll see what happens. Well, that's going to be x plus y, so x plus y times z. And recall that the plus operator that takes a fraction and a fraction returns a fraction. So fraction plus fraction equals fraction. And then that means this is a fraction, and then fraction times fraction equals fraction. So this whole result is a fraction on its own. All right, so x plus y all times z is 138 over 360. I will leave it as an exercise to the viewer to verify that that is indeed the correct answer. And then in the next video, we're going to talk about, hey, this probably is a simpler fraction than that. Is there a way I could reduce it to lowest terms?